Welcome to Heavy Networking, the podcast for people with opinions about packets and cable color. I mean, definitely about cable color because red cables are the fastest. I think we can all agree on that. I am Ethan Banks, your co-host for today's adventure, and I mean that we are going to some unusual places in this episode. And Drew Conry Murray is your other co-host. You can find us on LinkedIn, Blue Sky, and the Packet Pushers Community Slack group. Please follow us in those places and say things to us there if you like. Our guest today is Scott Johnson, the primary packeteer at Spacely Packets. And what Scott does is deal with networking in outer space. How do we get network traffic from the Earth to a lunar base or Mars or Europa? And then how do we get it back? And the problem, among other things, is latency. And the answer is not TCP/IP. The answer is it's complicated because this is a complicated problem to solve. And Scott, along with a lot of other folks, have been working on it for many years at the IETF and the Interplanetary Networking Special Interest Group, aka IPNSIG. So, Scott, thank you very much for coming on to educate us about the problems and solutions tied to, of all things, interplanetary networking. So let me set you up with this first question, Scott, because many of us network engineers, we got experience with global networking, right? We've built WANs that maybe go around the globe. Maybe we've even worked with like low Earth orbiting satellites, even higher satellites. But networking to other celestial bodies is not something most of us have run into. So would you explain the problems that network engineers and protocol designers are faced with in this scenario?
Yeah, absolutely. Hi Ethan, hi Drew. It's really good to be with you guys today. And
Me too.
you know, it's a distinctly challenging environment because you have a lot of different variables that you just don't have on a terrestrial network. You've got the situation where you have high latencies, right? And there's kind of a, I don't want to call it a barrier, but to paraphrase the film The Right Stuff, there's a demon that lives at about 3 seconds on your round trip time, right? The latency to the moon is just a shade under that. So we could potentially use an IP network, but there are other considerations as well, like when you have packet loss and the retransmission over those kind of high latencies, your what you call your good put really goes down like
Mm.
significantly when you lose any packets at all in those kind of links. So this was realized in the late 90s, believe it or not. As the internet was growing through the dot-com boom, and we realized, oh wait, we're going to have a shortage of IP addresses. It was also realized that we had a situation where we could not reach many of the places we wanted to reach. Between the latency being a chief problem, a secondary problem is a non-contiguous end-to-end path, right? We're used to having fast, reliable, constant connections all day, every day here on the Earth, but that's just not the case in space, especially when you start to get into deep space. So, if you can imagine you have a lunar lander on the far side of the moon, plainly, there is no chance for a direct connectivity from the Earth to that asset, right?
Because the
Maybe
far
you
side of the moon is always facing away from the Earth, so there is no line of sight between that far side landed lunar orbiter and the Earth.
precisely. Plainly, there's no opportunity for a continuous path there. Now, you can have something sitting at a Lagrange point, for example, that maybe you can do a bent pipe to. But what we realized was that a store and forward mechanism was necessary in the network in order to be able to reach a location like that. So fundamentally, you would have a connectivity from the Earth to maybe a Geo or a Leo constellation, and then from there to a lunar orbiter that, as it passes around the dark side of the moon, it makes its contact with the asset on the surface, and then can receive any bundles, what they're called, that are queued for transmission from the surface, and send any bundles that it has queued for transmission from Earth.
The keywords I heard you say there were store and forward. So literally, we're going to talk about the bundle protocol along the way here,
Hmm.
but a bundle that is stored at some intermediary point until it can be relayed to the next point, until it could be relayed to the final point, something along those lines.
Absolutely. If you look at the way our routers work, we have caches in our routers, obviously, but we don't have the kind of massive storage you would need to cover a non-contiguous circuit. There's one other factor that affects the difficulties in deep space as well, and that is space weather. Not a lot of people really pay much attention to it, except when there's a power outage in Canada or a satellite outage because of it, or the northern lights are visible from where they're at, right? But space weather is a big thing. You've got hot, uh, energetic charged plasma that's moving at incredible speeds through the solar system, and that induces currents in anything that it touches. So not only does our hardware have to be hardened against that, but we need to be aware that sometimes we're going to have RF blackouts in circuits because of these factors. And we need to be able to say, oh, look, the circuit didn't make it. We need to retransmit. Now, that's a thing that the internet can do, but not at these kind of latencies. So every node in a bundle network essentially also acts as a router for the most part, unless it's just a far endpoint. And it's also designed to have the capability to store that data in a way that will survive, say, a solar flare induced reboot of the machine.
Mm.
So there's a concept called SDR that you can write your data flow into memory for storage, but you can simultaneously write it to disk. So it's been designed to never lose any data at all.
So I think you've, sort of hinted at some of the issues, but why isn't TCP/IP applicable to this problem set with a few tweaks here and there?
Well, it's not just TCP that is the problem. As an IP network at the network layer, it it could work, but TCP tends to time out and have this aggressive delay system on retransmission where the delays increase as they go
Mhm.
every time you retransmit. So TCP breaks basically a little bit past the moon.
Well, okay, you're talking about the sliding window algorithm.
Yeah,
I'm
exactly.
guessing, right? The sliding window
Exactly.
is gonna go back shut because of retransmissions, and then and from an algorithmic perspective, when you get into a latency of what did you say it was, but to the moon 3 seconds, something like that.
It's 2.6 seconds round trip time.
That now we're at a point where TCP that and the sliding window algorithm is just not able to accommodate a latency that's as massive as that. That's where we're at.
Exactly. And then there are problems that happen further up the stack too. Like the way we write our applications are based on the notions that we have continuous low latency, high speed connectivity. And we can do things like handshaking, checkpointing, heartbeats without any problems in the transit of those packets. But the design for delay tolerant networks of applications is distinctly different. We have to make sure that like DNS is never going to work right to Mars. Even if you had a network on Mars and you make a DNS query from Mars to the Earth, you're looking at between 8 and 40 minutes of round trip time, right? So that's yeah, exactly. That's going to time out. And then you also have the situation where you may get a stale record even if you're able to find a way to pass it back and forth, right? Even if you tweak UDP so that there's no challenges involved in that and your timeouts don't happen and etc. um you still run into a situation where I may request the address of a resource on Earth, and I get let's call it, an hour later, I get the response back on Mars, and now I try to make an IP connection to that resource I just looked up, right? Well, that resource, if it's on mobile IP or if it's any cast that's up and down in some locations, you may wind up with a stale record that just doesn't reach where you're trying to reach. So all of this was realized in the late 90s, which is what put Vint Cerf and Scott Burley and Keith Scott and several other folks on the track that we need to design a dedicated set of protocols to handle these issues. There's actually an
Well,
excellent textbook from the IETF Delay Tolerant Networking Group chair who works at the Johns Hopkins University Applied Physics Lab on designing applications for delay tolerant networking.
I guess the big question I have though is like we've been sending signals into and from space, satellites, the moon, and so on since I guess the 50s, right? So,
Yep.
and we're getting telemetry from satellites, we're getting data from satellites. There are satellites, at least one satellite now beyond, the sun. And that's working. Why do we need to apply kind of a networking mindset to space communication?
Well, that's a really excellent question. If you look at the way the Deep Space Network works now, it's like the early internet in a form and fashion, in that before there were routers, all the TCP/IP links were simply point-to-point links, right? Um, and then we had Cisco come along and solve that, among others. But the problem with the Deep Space Network is it does create just that point-to-point links based on time slots. So if I have a contact that is, I've reserved, say, 20 minutes on the Deep Space Network to make that contact and to, get my telemetry, upload my commands, get any science data that may be up there. If I have a coronal mass ejection that is impacting the Earth at that time, my entire contact is gone because of the RF blackout that's going to come from that coronal mass ejection. I just have to wait until I am scheduled again before I can speak to anything. Whereas with the network, I could simply send my data as soon as available, along with everybody else's data that's on the same stream, going to the same next hop that can take
Okay.
it to the next hop to the next hop. So we wind up with an oversubscribed situation in the Deep Space Network simply because of the huge number of CubeSats and other small satellites that are being launched now. Like, the Deep Space Network was never designed to do anything beyond what NASA needed, and it was oversubscribed just for NASA's needs. So now that we have it being leased out basically to a lot of different commercial entities for their purposes, it's massively oversubscribed, both in terms of capacity and time slots.
So the idea is that we essentially built out a system for dedicated point-to-point communications, and an interplanetary network would allow for more of a shared medium kind of use.
Absolutely. If you consider that you, as a BGP speaker, could only talk to those direct peers that you have, right? That would be the situation that is a non-networked deep
Okay.
space. Whereas,
Yep.
make sense?
Yep.
Well,
Yep.
Scott, tell me if this is a bad analogy or not, but it reminds me of the transition we made from actual circuit-based networking, to what we do now with packet-based networking, where we're sharing the matrix effectively by breaking all our message communications up into packets. What we're doing now in interplanetary networking, a bundle would, in that analogy, would be like a packet.
Absolutely. Absolutely. And that's an excellent analogy to going from a circuit switch to a packet switch network, is really exactly what is being accomplished with this effort. But with certain caveats. It's not packets we're sending, it's bundles.
Yeah.
And what's interesting is that we can tunnel packets through a bundle network, but that doesn't solve the delay, that doesn't
Yeah.
solve the disruption, and it doesn't solve the problems that are inherent with that in the application space, right? So it's obvious we want IP networks on the moon and on Mars and different places, because what the heck, we have this massive installed application base. And if those networks can work locally, like on the surface of Mars, for example, say you've got, I don't know, 1,000 colonists there in 20 years, and these are just numbers out of my tail, right? They're going to want to build a network and be able to use the same tools fundamentally locally that they use on Earth, as opposed to having to learn an entire new communication system, adding to the challenge of living on Mars.
But the Martian IP network they might deploy to support that functionality isn't going to be contiguously connected to the internet on Earth. It is going to have some middleman running bundle protocol, perhaps.
Absolutely. And in order to make applications work between those two networks, we can't create a situation until we get like a quantum wormhole or something that makes zero latency. We can't solve that situation with an IP network. So the bundle network has to sit as an intermediary. And in order for the applications to work back and forth, we use what are called application layer gateways, which are fundamentally handlers for different protocols that they accept the say terrestrial request to send an email. Okay, they accept the email for the off-world domain, and they say, okay, we're going to turn this into a bundle payload. We're going to send that off to the Mars network. When it reaches the Mars network, it just makes a new email based on all of the payload and packet or mail headers, and sends it off to its final destination. So we have been able to achieve a level of interoperability conceptually between these two isolated IP networks, right?
Okay, no, we gotta take a step back because we keep talking about the bundle protocol and uses for the bundle protocol and some of the terminology around the bundle protocol, but we haven't talked about the bundle protocol yet. It's in an introductory way. So Scott, why don't we take a step back and do that? What the IETF has iterated on the bundle protocol. There's a few different RFCs that are out, and it was designed to support in part interplanetary networking and other sorts of hostile networking environments. Can you take that step back and give us that 10,000-foot view of what the bundle protocol is?
Bundle protocol is kind of unique in that there are dual standards bodies that are associated with it, right? So there's the IETF delay tolerant networking group, which you mentioned, which is the descendant of the Internet Resource Task Force DTN working group. And there is also the CCSDS, the Consultative Committee on Space Data Systems, which is a function, believe it or not, of the United Nations. So you've got two different groups that are slogging away at this, and there's a lot of overlap in the Venn diagram between the participants, but you've got the internet that does things the internet way, right? Loose consensus and running code.
Mm-hmm.
And it has developed certain standards, additions, and et cetera to bundle protocol, which that's RFC 91, 71, 72, 73, and 74 are the first tranche of bundle protocol related RFCs. But there are also things called orange books, pink books, yellow books, and blue books that exist inside the CCSCS. And with IETF being kind of an open forum, the CCSDS is a more of a multilateral governance model. So that is basically government only can participate in that directly. As a private industry guy, I can request from NASA observer status for that, but I can't go participate directly like I was a employee of NASA or JAXA or ESA or any of the other
Government space agencies.
space agencies that participate. Right, you basically have to be a government employee to get full rights in that. So it is always attempted to keep those two in sync. However, occasionally, things get shifted a little bit here or a little bit there. One example is a change to the naming scheme that we have for bundle protocol. So this is like analogous to an IP address, right? A node number. And these node numbers are used to represent, obviously, nodes on the network. And for the longest time, this was a 2-element encoding. So you had like 64 bits wide of node number space and 64 bits wide of service number space. And that is analogous to IP address and port. That's recently been changed to make a 3-element encoding. So you have 32-bit wide allocator ID, which is more now synonymous with an ASN, right? A 32-bit wide node number, which again is still analogous to an IP, and service number, which is analogous to a port. There's a little skew between CCSDS and IETF on this. IETF has led the charge, and CCSDS is a little behind in getting that memorialized in their documents. But just to throw that dynamic out there so that there is awareness of that, it is becoming more and more a multi-stakeholder environment. And we are actively pushing it to become that way because it's realized that not everybody that is going to contribute meaningfully to this network and process is going to be government-based. So, but let's get back more to the technicals. What is bundle protocol? Bundle protocol is fundamentally a store and forward networking mechanism. It's its own network layer. And it can act, well, I think we're probably going to get into this a little bit later, but it can ride over a lot of different protocols. It can sit atop as an overlay on the public internet. It can also speak things like AOS and Prox1 and specific space-related protocols that are not really in the purview of the IETF, but are designed and managed completely within the CCSDS. So it's difficult to navigate the governance, but the technicals all tend to align in practice, if that makes sense.
So is bundle then sort of like an encapsulation mechanism as opposed to like a data transfer mechanism?
Well, consider it as its own network layer with other components on top, right? And it can also sit atop an IP network. The method, it can speak a lot of different languages, basically, is what it comes down to. Like we can do this over RS-232. We can do it over Bluetooth as well. There are a lot of different layer ones and link layers that we can use to represent this. And when it is cohabitating with TCP IP networks or with IP networks, then it fundamentally acts as an application that sits on top of it. So the convergence layer says, yeah, I want you to listen on this port on this IP address for a TCP connection. And the bundles are basically encapsulated within the TCP packets or the IP packets at that point. However, bundle can run like just straight over Ethernet frames, for example, right? It can be simply encapsulated in the Ethernet frame. So it has the ability to move up and down the stack as necessary to adapt to whatever lower layers it has to ride upon. Like in developing the email solution, the interplanetary email solution, I realized that I had solved a problem that was a different problem in the internet. I was sending email back and forth from an IPv4 only address host to an IPv6 only host via a bundle network in between, because I have convergence layer adapters that speak IPv4 in one direction and IPv6 in the other, right?
Oh, okay.
I understand there's some things in that have been expanded in BGP that allows, you know, IPv6 routers to move IPv4 packets and et cetera without in basic transparency, and doing it at the application layer isn't necessary. But I just found it was handy, you know, that by accident, just in the way that I had deployed this, I was like, oh look, that one's v4, that one's v6 only, you know.
So thinking about, you gave us some essential concepts of the bundle protocol. There are nodes. There is a numbering system, kind of like analogous to IP addresses. It's a store and forward mechanism. It can, you know, ride on other layers of the traditional OSI stack. I'm curious, because you're dealing with issues like, you know, delay and very long distances. Does it have also a mechanism, because you're doing store and forward and you need to make sure the data actually gets to its destination, something like a way to confirm, yes, you received everything?
Yes, there is, but it's optional. So understand that there can be links that are unidirectional only. Okay, we only have a transmission window and we don't have a receive window from this thing. The contact time is not long enough that I can expect a transmission back. Okay. And in those cases, we turn off the reliability functions. But in other cases, we use a tool called DTPC, delay tolerant payload conditioning, that does a bunch of different things. It's got a lot of knobs and levers that we can switch. One of those is an ACK, an end-to-end ACK, right? There's also the notion of custody transfer, which is, say I'm on Earth and I have a bundle node and I send something to orbit, right? To low Earth orbit, to a constellation. Once it realizes that it has the whole payload, it can send an ACK back to me on that hop and say, yes, I got it. And then custody is transferred to the orbital node. And the same thing happens at each hop along the way. And fundamentally, what this saves us is the expense of end-to-end retransmission. And by expense, I'm not talking about money. I'm talking about network time, right? And capacity. Yeah. Because obviously, you know, we're not talking about the data rates, especially with RF communications, that we have on Earth either. So we have to be judicious in our use of network bandwidth. But DTPC does some other interesting things too, like in-order reassembly of fragments, for example. So it kind of acts like that transport layer on top of the network layer, kind of acts like TCP. But all of those functions can be turned on or off at will, basically. So if we don't need an acknowledgement for a certain quality of service, for example, then we just don't turn it on for that quality of service. But if say something that it's critical that we know that it got there intact, well, we turn it on for that.
So
case.
Lots of nerd knobs.
Oh, an incredible number of knob switches and levers that can keep you entertained for months at a time, just exploring what they all do.
Well, Scott, let's talk through some bundle use cases then. Now, we led with the sexy one, interplanetary communications. Ooh, going to Mars and the moon and Europa came up because you mentioned it in our planning calls. We were discussing this show.
Yep.
Is that the primary bundle use case? Is interplanetary comms? Would you say?
Bundle protocol was primarily developed for the purpose of overcoming those rigors which are present in space. Yes. However, it has seen significant terrestrial application. I am on the board of the Interplanetary Networking Special Interest Group, which is also the interplanetary chapter of the Internet Society. We have several working groups underneath that organization, one of them being the Pilot Projects Working Group. There's a fellow named Samo Grasic from Sweden who chairs that group, and he has had a project running for some years now that uses bundle protocol and a special low power implementation of the LoRa stack, which is long range. It's like a chirp method of radio transmission. It's small bandwidth, small packet size, but it works pretty well over long ranges at low power. So he's got this network set up to track migrating reindeer in his general area. And this is not only useful scientifically now, but as a way to test a robust network that is on the moon. And you have things moving around, you have rovers moving around, you have people wandering in and out of connectivity. And so it gives us a way to simulate that without having to write a whole bunch of code to simulate the links coming up and down. You just hang these things off of reindeer. When they wander into range, you get your data that has been collected.
Not that you have to use bundle to solve that reindeer tracking problem. LoRaWAN is used as a transport for a variety of those. I've heard the cattle ranchers and so on using LoRaWAN to track their herds. But they weren't necessarily using bundle for that. But you found a great use case here that works on Earth that bundle happens to be applicable to, riding LoRaWAN as the radio signaling mechanism.
Well, absolutely, and using bundle there enables that reindeer to wander off for a long period of time and the data to continue to be collected and stored in the node that's hanging around its neck. And when it finally comes back into range, maybe 3 months later, you get all 3 months of data that has been collected.
Very cool. Okay, so interplanetary, yes, that was the point of it, delay tolerant, but there's earthbound scenarios as well. What about things that I guess I'll put it in the middle, like well, we've been tracking the Voyager probes that NASA sent out in the 1970s, and they're in deep space now. I assume their technology is not they can't flash them up to bundle protocol, but they have their unique way that they're communicating with those. But could future deep space probes is bundle a good fit for something like that?
I can neither confirm nor deny that bundle is running on New Horizon.
Got it. Okay.
Or the Parker Solar Probe. I can't confirm or deny that it's running on either of those.
Got it. Rockets that would be in transit heading to Mars. This moving object that with
Yes.
the changing speed could be accelerating and decelerating as they leave Earth and then get to their destination. That's all okay. Bundle fits well here. It seems like it should. I hope I'm asking a rhetorical question, but yeah.
Absolutely, it
Yeah.
does. And we've actually made special accommodations to allow internet service interoperability with those free-ranging spacecraft.
Hmm.
So emails, webs, chats, something like video streaming, yeah, maybe not. But certain services we can make interoperable in that fashion through the bundle network with local daemons that are running on the spacecraft. And you can imagine you may have a larger IP network that's built out on the spacecraft, right? And you need to interact with that. One of the things I'm writing now is actually the application layer gateway handler for secure shell, so that we could get an interactive shell and have it work and not have it time out across these high latencies.
Well, wait, that doesn't work though. Well, okay, so I want in my brain it doesn't work, but you're saying it does. So explain that to me, because like Secure Shell or Telnet, anything like that that's real time and interactive is so latency sensitive. So how does putting bundle in the middle help with that problem?
This is an interesting thing, and it's the code that I'm actively working on right now. Fundamentally, it'll work like this. You'll log into base.mars, right? You'll SSH base.mars.
That is a server. I'm at a Martian base. I'm logging into a server that is in physical proximity to me. It's there with me on the surface. You're saying
No. You're on Earth. You're on Earth.
Okay,
right?
okay.
And you're trying to SSH into base.mars.
All right.
Okay. And so you have not only a variable latency depending on orbit, right? But you also have the situation where part of the year you're blocked out by the sun entirely.
Yeah,
right?
because that is on orbit, meaning Earth's got an orbit, Mars has got an orbit. Those two planetary bodies are going to be various distances from each other, depending. And so my latency could be who knows what, all depending on what time of year it is.
Exactly. Okay. One-way light time is between 4 and 20 minutes generally. Wow. In those instances where we can make contact. So you would log into a application layer gateway that is listening as Mars.base on the Earth, right?
Okay.
And you would be presented with a special shell. And that shell would say, okay, you want to connect to Mars.base, confirm what username, what password, or alternatively, what key do you
Mars
want to use?
1, 2, 3, 4, baby.
Yeah, exactly. Let's make sure that let's make sure we don't forget it, right? So what happens then is, okay, now this new shell says, okay, you're good to go. And it redirects IO to the bundle network. So when I send the command into the bundle network, the first bundle that is sent includes the end destination, the username, the password, etc. And before you start worrying about this being passed in plain text, we have a thing called BPSec that's built into BP. So we don't have to like stack security on top. We baked it into the architecture. Yeah, it's a lot easier than having to, deal with DNSSEC and IPsec and NTPsec, and all the other things that we bolted onto the network to overcome the lack of realization that people were going to be doing nasty things and this network is going to be available to everyone, right? So now this command is sent to the bundle node that is on the surface of Mars, the gateway node there, the application layer gateway. And it creates, based on the data you sent, a new SSH connection to base.mars.
Well, okay, but before you develop that, there's a big thing that I think just happened there. Mars is between 4 and 20 minutes away, hours away, whatever the distance is, right?
Yep.
So
minutes, yeah.
Minutes. Yeah. Okay. So I'm sitting there. I typed commands in that got bundled up and then shipped to Mars over that period of time. And I can't do anything until I get a response. Right? Or am I missing something?
No, that's absolutely right. You still have the latency in the middle. What the application layer gateway allows us to do is not have the circuit timeout in the process.
Because
while we still have to wait for the propagation delay, we still get our standard out from our remote secure shell session back over the bundle network delivered to our local session. right? We send a new command, it goes, it executes, whatever standard out comes back to us. So is it ideal in what we want? No. And like I said, the only way we're going to get the ideal, what we want, the way it works on Earth, is if we figure out how to make a zero latency quantum wormhole and deploy one on Mars and one on Earth. And that's, some physics work that's, depending on the amount of money or effort or attention paid to it, between 30 years and 150 years away. So I'm going to design for the missions that we have upcoming, and use the best effort to provide the services that we can make work.
You did sell it to me though, Scott. I get it. So with that SSH, whereas I'm used to a real-time interactive session that effectively is a character at a time, more or less with what's going on. I'm going to take all those one characters at a time, grab a bunch of them, put them into a bundle, the application layer gateway doing some understanding protocol and handling certain things for me, being a proxy, if you will, so that it can take my username, my password, and or a key if I'm using key instead, and then grab all that, bundle it, send it up. That hopefully I gave it all the correct information, and so that the bundle I'm going to get back from the server that's on Mars once delay propagation is over is, hey, you're logged in. Here's a prompt. And now I got my prompt back, and I can issue a command, and whatever my command is, or I can say invoke a script or something. Okay, that's all going to now get bundled up, not one character at a time, but all of that into a bundle, shipped off to Mars. It's going to run, it's going to do whatever it's going to do, and response is going to come back, and then that's going to get put into a bundle and then sent back to me. And now my screen's going to paint on this end based on everything that was in that bundle, as opposed to what the typical SSH experience is, which is effectively one character at a time.
Exactly. And what made me realize this would work was some of the work that I did over the past decade in the middle of the Pacific. Before I was working on space networking protocols, I was developing solar powered Unix terminal servers and terminals that we would place on very remote islands in the Pacific. And often, the uplink would be like 128K VSAT link, right? That had to go up from the island and then down to Australia, and then sometimes up to a satellite again, or sometimes via fiber back to me in Florida. So the latency was savage, right? And I would place these networks, and I'd often be out there for a month at a time. But as you know, a month is not enough to take a basic user level understanding and turn it into somebody that can operate a Unix, right? So I found myself for several years with the task of remotely administering these networks for these folks as they were trained and gained the level of knowledge necessary to operate them themselves in a consistent, reliable fashion, So, I mean, it was painful. It was like the old BBS days where you would sit and watch one character come in at a time. You know what I mean? You've got 11,000 people sharing 128K connection. and you're trying to administer that network in band.
Low bandwidth, high latency, the worst of all possible worlds. Wow.
Exactly. So it was that experience that led me to believe, well, you know what? They can just deal with the latency to Mars or the latency to the moon or to, wherever they happen to have it connected to, if it actually still works, right? And what can I say? It is the beginnings of this.
Yeah.
Surely there will be further optimizations that come along. Surely there will be improvements that can be made. But for initial, best effort type of projects, I think we're moving along at a reasonably quick pace on this.
Quantum entangled terminals, one on Mars, one on the Earth. That'll do it.
That's what I was thinking.
Yeah. It's just, yeah.
It certainly will. Well, the problem is you break the entanglement when you try to affect one or the other. So when you try to signal over it, your entanglement's broken, right? And the latest research on this, believe it or not, comes from D-Wave, quantum computing company, and Google worked together to demonstrate that entanglement was indeed a situation where a quantum wormhole was created, right? But you still have no aperture there. You still are gonna have a problem when you try to signal across it. So the latest thinking, the state-of-the-art thinking in this process is if we can entangle something like a single ring of graphene, right? 6 carbon atoms in a hexagonal lattice. That gives us an aperture in between. And if the wormhole works in such a way that it creates an event horizon in that aperture, then we can send a very high energy signal through, like an X-ray or something. We wind up with a Faraday cage situation, where the aperture is not big enough to fit the wavelength of, say, RF or even optical light. But the aperture, if it can be made big enough to pass some manner of an electromagnetic signal through it, then theoretically, as these two wormhole endpoints fundamentally fold space between them, there is now zero latency between these two endpoints, and we can just network in between. But that's kind of off in the deep end of theoretical physics as applies to this problem. If somebody gives me $1 billion, I'll work on it, but I don't think I'm going to be able to do much
Yeah.
with less than that. So
I think it was also a plot in Star Trek Next Generation or something too. So yeah.
It's entirely possible, yeah. We may wind up finding ourselves time traveling and doing all kind of crazy things.
You're describing that, and I'm realizing you're quite serious with what these experiments are. You and using these words that, right? And when we were growing up, all of us, this was purely science fiction, and now it's actually becoming reality as we begin to understand these things better and better.
Isn't that surreal?
And I'm going,
Isn't that,
I thought networking was the coolest thing in the world. And what you were describing, it's like, man, everything I thought I know just got boring. This is quantum entanglement and wormholes just make wow, that's interesting. Okay, where do we go from here?
So, wait, now let me jump back to a different problem we have with space networking, since we're getting into the physics end of it. Time doesn't flow the same everywhere. Time flows a little bit faster on the moon because it's not as far down a gravity well as we are here on the surface of Earth. And general relativity tells us that the further down a gravity well we get, the slower time moves. Just as special relativity tells us the faster we are going, the slower time
Wait,
moves,
so you're saying
right?
we can measure time when we measure time, it's different on the moon than the Earth?
Absolutely. If you take 2 identical atomic clocks, place one on the surface of the moon and one on the surface of the Earth, the one on the surface of the moon is going to be about 56 microseconds per day faster than the one on the surface of the Earth.
Which is significant.
And that doesn't sound like a lot.
No, that matters though.
It adds up. I mean, especially when you're talking about a mission duration of 10 years, 20 years, right? You're expecting your hardware to last that long. It adds up over time. There has been significant skew in the clocks of both the Parker Solar Probe, which gets real close to the sun and therefore is way down the gravity well, but it's still moving pretty fast, and the New Horizons. We measurable, good clocks show a significant difference in those things. So we have to be able to account for that as well when we're designing these networks, which is an interesting, particularly in like where we're pointing our antennas, right? Because if the antennas are not pointed correctly at the correct time, you're going to lose part of your contact time, or you're going to lose all of your contact time, right? If you have something that's moving very fast. Like, consider a laser transmission to Alpha Centauri. We have to aim where it will be in 4 years when we transmit.
These are the coolest problems ever. I love this. It's terrifying, but also just so interesting. Wow. And so therefore you have to understand how time is moving in relation to where the probe is in any gravity waves, gravity wells, as you've described it, that might be encountered.
And the velocity that the probe is moving, yeah. Or the velocity that whatever craft is moving, because that has an effect on the time base as well.
It's a whole new wrinkle on a train leaves Paris and a train leaves, right? When will the trains meet? Wow. Well, Scott, perhaps a question that's a little more tedious, a little more pedantic. That's about governance. So the internet's got governance to manage things like NetBlock assignments and ASNs and so on. Well, okay. Do we have governance for interplanetary networking?
We have a little bit more now than when I started. And that's going to be an interesting story that I can tell you part of, but there's enough to get the punchline out of, okay? So many years ago, when Bundle Protocol was first created, and the registries at IANA were made, right? Um, the registry for CBHE node numbers was created, and the vast majority of the small encoded, meaning 1 byte, 2 byte, 3 byte node numbers, were allocated to a group called SANA, the Space Assigned Numbers Authority, which is kind of a tangential organization to the CCSDS, right? And this was made so that it could pass out node numbers amongst the space agencies and have uniqueness to those node numbers the way we expect with IP addresses. And some years later, as I began getting involved in this, I'm an ISP operator as well. A small one, only for research and development, multi-homed so that I can stand up to the hurricanes that hit Florida, right? So I'm familiar with the governance process very closely. I've been an Aaron Fellow. I've attended many NANOGs. I've attended many Aarons. I've participated in the policy development process. I'm really comfortable with how all of that works, particularly the multi-stakeholder nature. So I'm building this machine in California, and I set up a BGP router on it. I use Bird on this virtual machine, and I assign /48 a v6 to it. I assign a /24 a v4 to it. And what I'm looking for is places where there can be cross-pollination of concepts or even interoperability between IP routing and a bundle protocol agent, right? So at the time, the project's working group, we were just kind of squatting on some node numbers because they weren't connected to like the space bundled network. So we just used whatever we wanted, low numbers, because it was easy. And I realized I should probably be using real node numbers here, because my goal is eventually to test interoperability with some of this stuff with JPL, which was topologically basically adjacent to where I deployed this node in California. So I'm building this stuff, and I'm in a conversation with Vint Cerf over email and Scott Burley, who is one of the primary authors of Bundle Protocol. And I said, hey, how do I get some node numbers? And they said, oh, you got to go to SANA. But the problem is SANA is like the same as the CCSDS. You got to be a government employee to be able to participate and get resources and things. And I was like, well, that's going to be a real problem for me trying to participate in this network. And it's going to be a real problem for any other commercial entity that wishes to participate in this network. Now, there's a big push to have commercial space be built out to a significant range, or scale rather. And in that process, it only makes sense to me that if you want to build an internet, but nobody can get IP addresses, you're going to have limited success, right? And that's the analogy that we face here. So I went and I read the RFCs that created the IANA registry, and I looked at the policies, and I realized that there was this whole range of node numbers that was unallocated, and it was allocatable via first come, first serve. And I went, oh, sign me up, please. I found the little form IANA for generic protocol registration. I said, yes, give me 16,384 node numbers, please, for the use of developing interplanetary network to internet gateways. And they said, okay, here you go. We're good to go. Now, interestingly, several days later, the IETF took action that would eventually result in the RFC that turned those node numbers from 2-element encoding to 3-element encoding, which, had I not been paying attention, might have made my resources non-viable anymore, right? But being a participant in that working group, I made the necessary recommendations that, hey, not only do we need what you're talking about for scale, I agree with that, but you also need to respect the rights holders that already have resources. And by that time, it had grown to over a dozen, including universities and one CLIPS lander vendor, So we said, look, you must make this backwards compatible. And we did all the work to make that happen. And that resulted in RFC, I want to say, I'm sorry, I forget the number. But there is a new RFC that from the DTN working group that effectuates this 3-node encoding. In the process, I also encourage in the IANA considerations that designated experts review every application thereafter, both for what is now called the default allocator ID node numbers, which was the original registry I asked for, and the allocator ID registry, which is that first 32 bits that's synonymous to or similar to an ASN, right? So now there are strict governance policies that are expert review. Is it robust like the IANA process with a policy development process? No, not yet. And there are other resources that are going to have to be paid attention to. Like, for example, when we are talking about an IP network on the moon, it is desirable if that is IPv6, simply because of the IPv4 exhaustion, right? And for routing purposes, we're in the process of talking to the Number Resource Organization, the RIRs, IANA, ICANN, all the relevant parties to say, okay, if you're going to be deploying off-world, here's a dedicated block of IP addresses that this comes from, and those can only be deployed off-world, whereas the remainder of the IPv6 space gets deployed on Earth.
Wow.
Right? There is the issue of top-level domains for off-world assets. Right? At present, we use a .int address, which is created by International Treaty Organization, basically. The CCSCS made sol.int, and that's used for naming off-world resources. However, the concept of like hab1.base.luna.sol.int, that's an awful long domain to try to type to access a particular resource. So if that is more like hab1.base.moon, well, that's going to be a little easier. It's going to be something that I think, at least from the market response to queries that we've made, yeah, we would much rather have that than some long, domain name that we have to deal with. So there is the issue of that, and given the GTLD situation now, I mean, somebody could just go buy it. You know what I mean? Somebody with the relevant resources that can manage a DNS top-level domain or a root
a bunch
server.
of astronauts could land on the moon
there are groups out there
in 10 years and set up a base and set up a domain, and then somebody's going to pop up and be like, I already own that, and I want $1,000 for it.
I mean, okay, so the process for buying a domain, a top-level domain, is a little different than buying foo.com, right? You have to be able to prove that you have the infrastructure and can operate the infrastructure to manage a top-level domain or a root server. You also have to pay like $250,000 just to get in the door. So, yeah, somebody could.
So it'll be
do
Jeff
that,
Bezos who can say,
but
I already own that domain.
now, see, that's the thing. It's a contention of the IPNSIG that, or many of us at the IPNSIG anyway, I don't want to speak for the whole organization, but many of us feel that this is a thing that should be managed in a multi-stakeholder fashion in the same way that the resources that we commonly use in the internet are, right? The two pillars of internet governance are DNS and routing, or IP addresses and those resources required, right? So it makes sense to me that the governance of the .moon domains, there are specific policies that are going to have to be in place too. Like, you don't deploy .moon on the Earth. You don't deploy .moon on Mars, right? The only way you deploy those domains on those locations is as application layer gateways. So that's going to have to be part of the user agreement fundamentally. Or the terms of service for registering a .moon, ideally it's not going to be in commercial hands. We accept that it may wind up in commercial hands, but ideally, if we're able to put all the ducks in a row, it'll wind up in the hands of an organization like PIR or someone else that operates it in a multi-stakeholder nonprofit kind of way. Notwithstanding that, it is plainly a significant revenue source, right? The DNS is the endless stream of money that just keeps flowing and flowing and flowing forever. And obviously, an off-world domain is a premium domain, honestly, if I wanted it to be commercial, I would have already done it. I would have tapped on some shoulders at Nanog and said, "Hey, psst, you're going to pay for this, and here's why," and it would have happened. But I don't think that's the right path for governing these resources, right? Do we want to be the Federation or do we want to be Ferengi is what it comes down
to. Gold pressed latinum, baby. Yeah. Yeah.
Exactly. Exactly.
Well,
greed is eternal, No, not here.
All right, Scott, as a closing question, how can network engineers interested in interplanetary networking get involved? You've mentioned the delay tolerant networking group that's a part of the IETF. Perhaps there, other venues?
The delay tolerant networking group is an excellent place for the technicals and learning and understanding those concepts and contributing. The organization that I sit on the board of, the Interplanetary Networking Special Interest Group, which is IPNSIG.org, IPNSIG.org, is kind of the confluence of the thinkers in this space, right? We have things like the projects working group where there are active developers and network operators and things that can provide guidance and code suggestions in how to deploy these networks. We have an active network that we use and we have built amongst the participants there. So IPNSIG is a great place. I would highly recommend joining. It's very simple. You just join the Interplanetary chapter of the Internet Society. If you're already an Internet Society member, it's just adding a chapter. If not, signing up to become an Internet Society member is free. And then you join the Interplanetary chapter in that fashion. We have mailing lists. We have a couple of meetings that happen throughout the month on a monthly basis. There's a developers meeting that I host every other Friday at 6 o'clock for the experimental branch of ION, the Interplanetary Overlay Network suite of software that was originally produced by the Jet Propulsion Laboratory and Cal State. We have a massive library on the IPNSIG website. Well, it's linked on the website to the Zotero library, and this goes back, into last century of the design documents, the progress, all the papers that we run across, all the information that is available. We archive there in that location. So anybody wanting to get involved in interplanetary networking, I would highly suggest they join up with us at the IPNSIG, and all of the experts are convened there for the most part. And I mean, we're talking about, we have representation from JAXA. Our chairman of the board is actually a cultural attaché in DC now from Japan, but his involvement is direct with JAXA. We've got many of the pioneers, both retired and still working at NASA, that are involved. We have people from commercial entities that are developing both applications, and we have a networking guy from Intuitive Machines who is part of our group as well. It is the single best resource that I have found and been associated with, which is why I stood for the board and do outreach like this, among other efforts, because we realize that as a space community, there is not everything that is necessary to make the best possible interplanetary network, right? We need the internet community too.
Mm-hmm.
We need the knowledge. We need the skilled user base. We need the folks that can take the networking concepts they already have and understand, based on those, the networking concepts that are around DTN, and we need to deploy nodes and build things and gain operational experience for a lot of people
deploy
in this
nodes.
fashion.
I mean, real quick, you don't mean deploy nodes just in space. You mean I could, if I was interested, I could deploy a node that's useful somehow here on Earth?
You absolutely could. We've got the projects working group network that has been this for a long time. However, we're in the process of standing up the bundle bone. Similar to the IPv6 6 bone or the M bone for multicast, we're building a terrestrial bundle bone on top of a very high capacity research and education network. So we're going to be placing core routing nodes around the United States on this network initially. And this will allow us to have the kind of hardware in place that is necessary to exercise these networks. Like, for example, I've got a server behind me that has close to 300 terabytes of storage in it. It's a retired cache server from a streaming service. And this used to sit on a network edge at an IES ISP to cache the data for their users, so that, the standard cache model, right? Edge cache model. So we're going to be deploying some of these servers so that we can really exercise the store and forward for payloads like 4K video that lasts a minute and a half, that needs to be stored, say, 15 minutes before it's retransmitted. Now, in these nodes, we're also going to stand up virtual machines that will allow IPNSIG members. We can just allocate these to IPNSIG members for their research, testing, development, learning processes, and goals. Right. So, say you're a member of the IPNSIG and you're participating in the project's working group. By the first of next year, you'll be able to say, "Hey, can I get can I have a node, please, in Seattle?" And we'll say, "Yeah, sure. Here's your VM. It's turned on. Ion is already installed. You've been allocated a node number, IP addresses, and etc. And you can begin using that. If you need another one somewhere else, we can turn that on as well, so you can, actually test the network between two nodes that you control." These similarly can be networked to a node that's sitting in your lab there, right, or in your office, or in your home. There's no real requirement to be on the high-speed backbone to participate, but we felt it would be wise to have a high-speed backbone so we could exercise all these protocols at really high capacity and make sure that there's not a bug that's going to catch us when we can't fix it in space, right?
Well, Scott, this has been a fantastic conversation. There's so many resources and so on. But before we close here, how do people follow you on the internet?
Oh gosh, how do they follow me? I make it hard to follow me. I am on LinkedIn. I use that. I am Spacely Packets on Blue Sky. I use that. I have passed on using Twitter of recent for reasons.
Yes.
And generally I am so deep in the guts of a Unix that I don't have much time to surface to jump into user space to play with social media. But I mean, you can find my website at spacelypackets.com, and I'm always available and accessible through the IPNSIG.
Okay.
Anybody that reaches out to me in that capacity, I try to do my best to keep separation of church and state between my personal company, and this nonprofit that I participate in. And so I find up often wearing the nonprofit hat that I give away a lot of information that I probably could charge somebody for under my company. But in the long run, I look at it as an investment into the growth of the network. The more people we have participating, the better. Like I said, we need the internet involved simply because we're going to need capacity. Somebody's going to have to build backbone. Yeah, somebody's gonna have to fly stuff.
Yeah, this conversation was interesting to me, Scott, for lots of reasons. I mean, not just all the how nerdy this is, but it's super cool. But also because there's a practical side to this. This has been being worked on for over 2 decades now, trying to get to a point where we're solving the challenges of communications in space. This is a big deal. That's serious work as well as being just absolutely fascinating and interesting. So again, thank you, Scott, for taking the time to come on Heavy Networking today and talk to us about this stuff. And if you're still listening at this point, man, cool discussion. And I hope a conversation like this opened up your mind to thinking about hard problems that need solving and can't be solved with the tools you're used to using. But that doesn't mean that what you know about networking doesn't apply, right? Because your existing knowledge of how to move ones and zeros around definitely applies, but you just got to apply that knowledge in a new way. So as an aside, for fun, if you know what a who is, do a who is sol.int.
Oh, yeah.
I think you'll see some interesting names that you've definitely heard of before. And if you have if you've got a follow-up about this or any episode in the Packet Pushers panoply of podcasts for your progress as a packet professional, send them to me and Drew via packetpushers.net/follow-up. Until next week, like, share, and subscribe on whatever your podcast platform of choice is. We're everywhere, including Spotify and YouTube. And last but not least, remember that too much networking would never be enough.